Okay, hey folks, picking up right where we left off. I think that this should be the last video of our section on phase changes, but I've got a timer going, so we'll see how long this goes. It might end up being 2 if it goes too long. Okay. But now what I want to get into is how we can start predicting mathematically where these phase boundaries should appear. Okay. So for example, I'll remind you that when you look at chemical potential versus temperature, right, the slope of this line is entropy, right? And we noted that the vapor has a bigger entropy than the liquid, than the solid. So where we see these cross, that's where the phase transition happens, okay? So I derived an equation on the first lecture that was chemical potential as a function of pressure. So chemical potential of P final equals chemical potential of P initial plus RT natural log of P final, P initial. And in the case when P final is greater than P initial, if we just think about this and inspect this equation for a moment, then this means that mu will increase, right? Because if P final is greater than P initial, natural log of a number greater than 1 gives me a number greater than 1, right, times RT. And then that has an additive effect, right, because I get a positive quantity, okay? So when I increase the chemical potential of these, then I'm going to start seeing lines that look something like this. You know, maybe my solid line, it increases, okay? And then my liquid line, it increases, okay? And then you can see where they cross, I get a new melting point, okay? And so just as a general rule, if I look at this for 2 cases, okay, and here these are cases in which the density of the solid is less than that of the liquid and the density of the solid is greater than that of the liquid, okay? So in this case on the left, this is a case where I'll say the molar volume of the solid is less than the molar volume of the liquid. So this is normal, right? So this is a normal condition, most things, where the solid is more dense than the liquid. Or in other words, the molar volume of the solid takes up less space, right? So for the same amount of material, that means it's more dense. So what you see here is a smaller effect on the increase of the heat capacity of the solid, but a much bigger increase on, I said the heat capacity, rather, I meant the chemical potential. But there's a much bigger increase of the chemical potential of the liquid. And as a result, you notice here that the freezing point increases. So that is, most materials will have an increased boiling point with an increased pressure. So let's say as P increases, TF increases. But now this is a case in which the molar volume of the solid is actually greater than the molar volume of the liquid. So this is totally not normal. In other words, water, right? And so now what you notice, the effect here is that there's a much bigger increase in the chemical potential of the solid than there is of that of the liquid. And the result here is that the freezing point decreases with increasing pressure. So as pressure increases, the freezing point decreases, okay? So this is the case with most things. In other words, the solid doesn't really change that much with increases in pressure, which is kind of what we would expect. However, water is strange. Water is weird. And in this case, there's much more of a change to the chemical potential of a solid than there is in the liquid. And that's really what's driving those things for water, okay? So now how do we predict this for any range of increase of pressure and temperature? Well, this is where we get to what's known as the Clapeyron equation, okay? So here's my generic phase diagram P versus T with phase alpha and phase beta. And the boundary between those phase diagrams is given by dp dt, right? Okay, so whatever this relationship is, P versus T, or the change in P versus the change in T, that's going to give me that boundary. Okay, so we start by noting that the chemical potential, I'm going to say chemical potential of phase alpha as a function of pressure and temperature has to equal the chemical potential of phase beta as a function of pressure and temperature. So all data points along this line have equal chemical potentials. We also remember fundamental equation, dG equals VdP minus SdT. Okay, and we note that we can exchange free energy and chemical potential, right? We can make, they're the same thing when it's the molar Gibbs free energy. So now I'll expand on this relationship, okay, and I'll say that we're going to go to molar quantities so that we can connect. Remember, molar free energy equals chemical potential. So now if I look at the molar volume, and I'll just say molar volume of phase alpha times dP minus molar entropy of phase alpha times dt equals the molar volume of phase beta times dP minus the molar volume of phase beta times dt. So we just set those two things equal to each other, okay? And so now what I'm going to do is collect the like terms. So I'm going to do a little bit of algebra here, and I'm going to say SM. So I'm going to add, oops, I wrote volume, but I meant to write entropy. Okay, so I'm going to collect the entropies and the volumes on each side. And when I do that, I get SM of phase beta minus SM of phase alpha, all times dt. So add that over to that side, subtract V over to this side, equals molar volume of phase beta minus molar volume of phase alpha times dP. And I will note that this SM of phase beta minus SM of phase alpha, I'm just going to call that delta S of the phase transition, TRS. Okay? So that becomes delta S dt, and this, of course, is delta V of the phase transition, dP. And what we're interested in, right, is dP by dt based on this graph. Okay, so if I collect those terms here, then what I end up with is, so divide dt over, divide V over, I get delta S of the phase transition divided by delta V of the phase transition equals dP by dt. And noting that delta S equals delta H divided by T, I'll make a substitution for delta S there. And this becomes delta H of the phase transition divided by T, and that's, of course, T at the phase transition, TRS, times delta V of the phase transition equals dP by dt, and this is the Clapeyron equation. So this gives us the boundary between any phase, right? So it says dP by dt equals delta H divided by T times delta V, okay? And then we note that this is reversible because we start by saying set the two chemical potentials equal to each other. Okay, so I'm going to keep going. So let's apply the Clapeyron equation now to the solid-liquid boundary. Okay, so rewriting the Clapeyron equation, I'm going to start way up here to give myself plenty of room. dP by dt equals delta H, and now I'm going to say that's delta H of fusion divided by T fusion. Excuse me, now I'm just making a generic T so I can connect it to this T. So delta H fusion divided by T times delta V fusion. Okay, so the delta H of fusion is definitely greater than 0 because there's an increase in entropy when you go from a solid to a liquid. And the delta V of fusion for most things is greater than 0. So in other words, when you go from a solid to a liquid, the material usually expands because its liquid is less dense than its solid. Okay? And so what that means is you get a positive slope, right? Because we note that in this equation, right, it's dP by dt. So if delta H is a positive quantity and delta V is a positive quantity, dP by dt should be a positive slope. However, if we get a negative slope, delta H of fusion is still a positive quantity. So that means that if we have a negative slope, it has to be because the delta V of fusion was negative. So that's how we can tell in our phase diagram what are the relative densities between the solid and liquid phase. All right? So in other words, delta V fusion equals the molar volume of the liquid minus the molar volume of the solid, right? Okay, so now continuing along here, so I'm going to collect like terms in this equation, and I'm going to say dP equals, so I'm going to multiply T over to this side. Okay, delta H fusion divided by delta V fusion. And now we're going to keep the T's together because we're going to allow the fact that the temperature of fusion changes with changes in pressure. Okay? And so we're going to integrate both sides from condition 1 to condition 2. We're not going to make it final to initial. We're going to make it 1 and 2, and that's done as a means of a convention. Okay? We could say final and initial, but typically in phase equilibria, the 1 and the 2 is used instead of final and initial. Okay? And you notice because I took delta H of fusion and delta V of fusion outside of the integrand, for this derivation, we're going to say assume that those don't depend on temperature. So assume delta H and delta V are not temp dependent. They are, as it turns out, and we would need to have some equation of H versus T and V versus T. But in the derivation of this equation, those aren't going to be used. And in some conditions, this leads to not very much error at all. In other conditions, this leads to a lot of error. So I'll talk about when that happens. Okay? So now, but when I integrate this, what I get here is P2 minus P1 for this, right? And then over here, I get delta H fusion divided by delta V fusion. And you recognize that's going to be a natural log of T2 over T1. Okay? So now, and of course, to make this a useful equation, really it's going to be P2 equals P1 plus delta H of fusion divided by delta V of fusion times natural log of T2 over T1. Let's talk about units. Okay? So if delta H is in joule per mole, then that means delta V has to be in cubic meter per mole. Okay? Because a joule divided by a cubic meter equals a Pascal. All right? There's no other way around it, folks. I know we've been having a hard time with units this semester, but if you use joule per mole and cubic meter per mole, so because, right, remember, this is molar volume we're talking about, then your pressure units are in Pascal. Okay? And so now what I also want to point out is whatever T1 is, P1 has to match that. And whatever T2 is, P2 has to match that. So if you recall in general chemistry, when you didn't use this equation, you actually used the solid or the liquid vapor equation. You would typically pick things that are known. So for example, if you want to calculate P2, you have to know, or you have to say, well, I want to know P2 at some T2, right? But now you have to plug in a P1 and a T1 into this equation, all right? So typically for P1 and T1, you could use the triple point. So you could say whatever T triple point is, then you would use the P triple point, all right? If, let's say, you use the normal fusion point, then you would actually use the normal pressure of the fusion point, which would be 101.325 Pascal. So it would be the normal, 1 bar standard pressure. Okay. So actually, I should erase P fuse and write that as P standard. Okay. So in other words, you have to, if you want to calculate, and as we'll see with our Igor exercise, if we want to use this equation, we have to supply known values for P1 and T1, and they have to correspond, right? They have to be some, data point along that boundary, okay? So now what about the liquid vapor boundary, okay? So a few things, let's see, how much space did I give myself? Yeah, a few things on the liquid vapor boundary. No, you know what? I'm not gonna worry about that too much. I just want to get into the derivation. Okay. So we know that dP by dt equals our Clapeyron relationship, but this time it's going to be delta H of vape divided by T times delta V of vape. Okay. And now, as it turns out, the, let's see here. So, okay, yes. So as it turns out, the delta V of vaporization basically equals the molar volume of our gas, okay? So we know that technically, so I'm kind of doing this backwards, and maybe I'm having a brain fart moment here. So Vm gas minus Vm liquid, so we know that's true, okay? So the molar volume of, I'm just going to use water as an example. The molar volume of water is 0.018 liters per mole. I get that by assuming a density of 1 gram per milliliter. And if I say that there's 1,000 milliliters in 1 liter, and I know that there's 18 grams in 1 mole, and then of course you can see I'm going to have to flip all of that. But when I do that calculation, basically 1,000 divided by 18, I get 55.555 mole per liter. And if I flip that, if I do 1 divided by that answer, I get the 0.018 liter per mole. Okay, so that's where that comes from. But now what's the molar volume of a gas? nRT over P, right? nRT over P. And of course, at standard conditions, we recognize that that's 22.42 liter per mole. So compare those two numbers for just a second, right? 22.42 liter per mole versus 0.018 liter per mole. So basically, the delta H of vaporization is more or less just equal to the molar volume of a gas. Okay. So what this means now is the following. All right. So and of course, because we're going to change our pressure quite a bit, we can't just put a constant value in for the molar volume of a gas. So our equation changes. It becomes dP over dt equals delta H of vaporization divided by T, and I'm using here the molar, actually yes, the molar volume, so it's not nRT over P, it's just RT over P. Okay. So now we're going to replace that by saying RT over P. Okay. And of course, that all equals delta H of vaporization times P divided by RT squared. So I just did some algebra there. So I combine the T's, T squared. I have 1 over P, which just becomes P. And so this is now the equation that I'm going to integrate. Okay? So I've got dP over dt equals delta H times P divided by RT squared. So setting that up to integrate between P1 and P2 of now dP, so I divide over to P, okay? And now that equals delta H of vape divided by R. And we'll assume that, delta H doesn't depend on temperature. It does, and of course, under certain conditions, this will lead to small error, and other conditions, this will lead to large error. And so now this is, let's see here, dt over t squared. Okay. So from here, I get a natural log relationship. I get natural log of P2 over P1 from this integral. And over here, I'll just do the integration real quick. That becomes negative delta H of vaporization over R times, and it ends up being 1 over T2 minus 1 over T1. And this is the really famous Clausius-Clapeyron equation that you most definitely used in Chem 109. Okay? And so now to do a little bit more algebra here, if I take E of both sides and multiply the P1 through, so I'm just doing 2 algebra steps and 1 here. So E of both sides, and that becomes P2 over P1, and then multiply both sides by P1. Now I get P2 equals P1, and then of course I have the exponential of this whole thing, and I'm just going to say EXP of all of that stuff, negative delta H of vaporization over R, 1 over T2 minus 1 over T1. Okay, great. And so here is my famous Clausius-Clapeyron equation. Okay. And so just a few more notes on the liquid vapor boundary. Okay. So if I just look at this, I meant to have a bigger graph right here. So if I look at this P, which technically, if I'm just looking at the vapor, this gives me the vapor pressures at any given temperature. Okay. And there's a special condition when the vapor pressure is equal to atmospheric pressure, right? We call that boiling. Okay. And so we could interpret that any point along this line is a boiling point if that is what the pressure of the liquid is, right? However, if the pressure over the liquid, so right here's my let's say beaker of water, okay? So let's say I've got P ATM, and we know that that's pushing down on the liquid. Well, the liquid pushes back on the atmosphere, right? And that pushing back on the atmosphere is the vapor pressure, right? And so when those two are equal to each other, the liquid is boiling. But what about when the vapor pressure is not equal to the atmospheric pressure? Well, that means that the temperature must be less than the boiling temperature. And thus, any one of these data points, let's say, would give us the vapor pressure of that liquid. All right? And so, of course, this also predicts, right, as you increase the pressure over a liquid, you increase the pressure required to boil it, or the temperature required to boil it, rather. Okay? And so now the solid vapor boundary, okay, turns out that it's exactly the same. So this is for sublimation. Man, that doesn't look like it says sublimation at all. For sublimation. right? Going directly to a vapor from a solid. So it ends up being exactly the same as the previous case, the liquid vapor boundary, except for now you replace delta H of vaporization with delta H of sublimation. Okay, and you have the same equation that describes that boundary. Okay, and using all three of those equations, so this equation right here, this equation right here, and this equation right here, we can reproduce a phase diagram, right? So in other words, let me find like a fictitious phase diagram somewhere in here, like a generic one. Okay, right, so on our generic diagram, right, we derived the liquid vapor equation, that's that Clausius-Clapeyron equation. The solid vapor equation is the same as Clausius-Clapeyron, except for it's delta H of sub instead of delta H of vape. And then the solid liquid boundary line, we also derived. So that gives us all three of those lines. And that's what you're going to do in your Igor 3. Okay? And so the last thing that I want to talk about, let's see, did I get through all my slides? Yes, the very last thing that I want to talk about, the Ehrenfest classification of phase transitions. So I mentioned earlier there are first order phase transitions and second order phase transitions. Okay? So if we just look really quickly at what happens to all of the properties of a first order phase transition as a function of temperature. So for example, if volume, there's a huge jump in volume. It's discontinuous. Okay? Same with enthalpy. There's a huge discontinuous jump in enthalpy. So these lines right here on this graph mark the transition. So we'll say TRS for transition. Okay? As it turns out, the chemical potential just falls off smoothly. And that's because if you remember, right, this line for one phase would just continue along, right? And for this other phase would continue along. So the chemical potential just has that sharp point. But just like in enthalpy, in entropy, there's a discontinuous jump in a first order phase transition. And the result of all of this is the heat capacity at the phase transition becomes infinitely large because you are technically supplying heat without a change in temperature. So all of these things, as you might guess, what is a first order phase transition? Well, a solid to a liquid or a liquid to a gas, right? Okay, so these are large scale changes, right? So in other words, when you look at the entropy change of a liquid to a solid, there's a huge difference. Same with the enthalpy, okay? Same with the volume, as we just discussed. And so that means the heat capacity for those first order phase transitions is infinite, technically, at that value. So what about a second order phase transition? Okay, well, notice that there's some differences, right? So the volume, it has kind of this like discontinuous function thing going on, but not this big gap, right? So it's a much smoother change. Same with enthalpy. Same with chemical potential. There's a really smooth change. You can hardly tell a difference in the chemical potential in a second order phase transition. Same with the entropy. And the heat capacity, there is a discontinuous jump, but the heat capacity is technically not infinite at that value. Okay? You notice that it actually drops pretty dramatically. So in other words, as you might start guessing, second order phase transitions aren't really these large scale changes. They're actually like solid to solid transitions. So like from one crystal structure to another crystal structure. Okay, so perhaps from like, you know, a BCC unit cell to an FCC unit cell might be a second order phase transition. So very slight changes, right, in the volume or the delta H. So like in all of those water phase, that water phase diagram I showed you, all of those different solid phase transitions, those would be second order phase transitions. Okay. Now, what about the in-between region? So I'm going to kind of put like a squiggly line. There's an in-between region between first order and second order phase transitions, and I'll call that the lambda line. Okay? And let's go back to helium for 1 second. Let's go all the way back. Yes. Look, here's the lambda line for helium. So as it turns out, the phase transition between a liquid and a superfluid, it's not quite first order, but it's also not quite second order. Okay? And the reason why it's called a lambda line is because if you look at heat capacity versus temperature, it actually makes like the shape of a Greek letter lambda in the thermogram. So it looks like it wants to be infinite, but it also quickly recovers. So it's kind of like has some characteristics of a first order phase transition and some characteristics of a second order phase transition. Okay? So the lambda line is in reference to things that are in between. Okay? So definitely from a fluid to a superfluid, fluid to a superfluid is one of these in-between type of phase transitions that would have a lambda line, such as helium. Another interesting example is actually the transition between transitions between ferromagnetism. So there are certain materials that under certain conditions of temperature and pressure can change their magnetic properties. And so that has somewhat similar, ideas of a solid-solid phase transition where it's going from like different crystal structure. But as it turns out, there's fairly large differences in its volume and enthalpy and entropy. Okay, so magnetism would also exhibit a lambda line. Okay, so most of the phase transitions that you've seen up to now are these first order phase transitions. Okay, when you have these really interesting solid-solid phase transitions, like different crystal structures, those are second order. And these very few rare examples like fluid to superfluid or the change in magnetic properties, those are somewhere between first and second order. And the telltale sign is the lambda line in the heat capacity. Okay? But most of the time, when you're observing heat capacity in a second order phase transition, you're going to see this like kind of discontinuous looking gap. Okay? All right, folks, so I think that covers it pretty well. Hopefully my injured brain was making some amount of sense there. Please reach out to me for questions. If you have any, I'm sure you will. I will see you all on our live meeting on Friday or office hours. All right, folks.